Hello. Uh, Hello everyone. So this is Prasant. Can you hear me?
Yes, sir.
Yes, sir.
Yeah. Okay. So as we have sent an announcement also, so please, actually, ma'am will cover the concept related out random variables and distributions. Uh, I mean, make a pace with ma'am and don't ask the questions from activity, practice, and graded. If you have any problem, uh, any problem in any question related to those topics, so you can ask in upcoming session which we will take from Monday, Tuesday onwards. Okay, is this okay for everyone?
Yes, sir.
Yes, sir.
Okay, yeah. So
Yes,
don't
yes.
ask specifically if you have doubt in that any concept, so you can raise your hand and I will take. Okay, yeah.
Yes. Thank you, Prashant.
Thanks ma'am.
Yeah.
Yeah, we can
Thank you.
start.
Thank you, Prashant. Yeah. So as Prashant has told, this session is a revision session wherein I'm going to try and revise the concepts, and you can see the list of concepts is pretty long. I'm going to start by revising the concept of a random variable and then look at specific discrete distributions and a few continuous distributions. So let's have some ground rules. You can, I will not be attempting, or I will not clarify any assignment or any other question that is there. That would be handled by the team. However, if there is any doubt at a conceptual level, please feel free to stop me and ask me. You can use the chat box. I'll be going through the chat box. I think Mayur is also going to join us in some time. We will be looking at the chat box and we'll answer. Perhaps every 15 minutes, I'll have a look at the chat box and I will answer the questions. I hope that's okay with all of you. Yeah. Yeah.
Yes, ma'am.
As always, the slides are always shared post session. Okay, the slides would be shared, but there is nothing new that I'm going to tell in these slides. These slides are already available for the students who are enrolled into the program. So there is nothing new, but this is only going to be a revision session. So are we good to start?
Yes, ma'am.
Yes, ma'am.
Okay, right. Thank
Yes,
you.
ma'am.
So the purpose of this session is to revise the concepts of what is a random variable, how do we define a random variable, what is a probability mass function. So we will go one by one, and at any point of time, I repeat, if you have a difficulty in the conceptual level understanding, please stop me. I will repeat it. So if you go back to the probability concepts, the building block of the probability was we started with what was a random experiment. Once we said what was a random experiment, we defined what was the sample space of a random experiment. Okay. Now, when we defined the sample space, we saw that the sample space could be of a different type. For example, if I toss a coin twice, my sample space was HH, TH, TT, HH, HT, TH, and TT. If I'm looking at tossing a coin till I get a first head, then my sample space was T, H, H, TH, TTH, and so forth. If I'm computing the time taken to reach from point A to point B, it could be any time which is between 0 and infinity. If I'm looking at a dartboard, it could be any coordinate x and y such that x is less than or equal to 1 and y is less than or equal to 1. So we defined different types of experiments and we listed their sample space. Now, sometimes we might not be interested in the outcome of the experiment, which is given in the sample space, but we might be interested in mapping, or we might be interested in the function of the outcome. What do I mean by function of the outcome? Suppose I'm counting the number of heads. Rather than knowing whether the outcome was a HH, HT, TH, and TT, I'm counting the number of heads in every outcome. Then I'll map this outcome to 2. I'll map this outcome to 1. I'll map this outcome to again a 1. and I'll map this outcome to a 0. Similarly, if I'm counting the toss in which my head appears, I'm going to map this outcome to a 1, this outcome to a 2, this outcome to a 3, and so forth. Similarly, if I'm interested in knowing whether the time taken is less than or equal to some particular value, then it is 0 is less than or equal to less than 5 minutes, then this is going to be 0, an interval 0 to 5. So you see that the way I am defining is I'm not interested in the outcome itself, but I'm interested in a function of outcome. And that is the first thing I'm going to refer to as a random variable. So I repeat, when we are not, often we are interested in all the we are not interested in all the details, but we are interested in the value of some numerical quantity. That could be the number of heads or number appearing in the rolling a die and all of that. Or if I roll a die twice, I might be interested in what are the sum of the outcomes. For example, if once, then I might be I'm not interested in actually whether it's a 1, 6 or something, but I might be interested in mapping each of these outcomes. This is mapped to 2, this is mapped to 3, this is mapped to 3, this is 4, 4, 4. So I'm not interested in the outcome itself, but a value of some numerical quantity that is determined by result. These quantities are formally actually real valued functions defined on the sample space. Let me explain this. See, for every outcome, I'm mapping a real valued number. So when I'm mapping for every outcome a real valued number, I can think of these quantities or numbers as real valued functions defined on the sample space. And hence, a random variable is a real valued function defined on a sample space. Is this definition of a random variable clear, please?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah, that is the first key understanding is I'm not interested in the outcomes itself, but I'm interested in some quantity. And this quantity is what I am more formally defining as a real valued function defined on the sample space. Now, the minute I define a real valued function, for example, I toss a coin twice and I know that these are my outcomes. Now, is this definition unique or can I have more than one definition? That is the natural question I can ask. The answer is I can have more than one random variables. For example, the first random variable I could define is the sum of the outcomes. So it's mapping 1, 1 to 2, 2, 1 and 1, 2 to 3, 3, 1 and 2, 2 and 1, 3 to 4 and so forth. I could also be defining a random variable which is lesser than the two outcomes. And if the outcomes are same, I call it the same outcome. So this is mapped in that case to 1. These two, everything here and everything here is mapped to 1. Everything here and everything here is mapped to 2. Everything here is mapped to 3. Everything here is mapped to 4. These are mapped to 5 and this is mapped to 6. So you can see that every outcome is again mapped to a real number or a quantity of interest. So we are having, so the fact that we have established here is on any sample space, the random number that is, or the random variable that is defined is not unique. I can define many random variables. So the next question we are asking is, okay, I have defined random variables. So what next? So I might be, just as I was able to assign probabilities to the events, now I might be more interested in knowing, because it's a random variable, what is the chance with which that random variable takes the value? Because I'm assigning a particular value to every random variable. So it makes sense for me to ask this question. What is the probability with which the random variable takes that particular value? Yes. So to ask, is this clear? This is what I'm interested in knowing. I
Yes,
know
ma'am.
that
Yes,
this
ma'am.
random
Yes,
variable
ma'am.
takes multiple values. And
Yes,
now
ma'am.
I'm interested in knowing what is the chance with which the random variable takes that particular value. to answer the probability with which X takes a particular value. Again, what we are going to do, we are just going to map the outcome. So if you look at every outcome, X is the sum of two rows and Y is the lesser. Every outcome is mapped to a value of X and Y. Now I'm interested in knowing what is the probability of X taking the value 2. If I look at probability X is taking the value 2, I know the relevant event is only this. X equal to 3, the relevant event. So I know already I have learned in my earlier module how to assign probabilities of events. So now what I'll do, for every value this X is taking or Y is taking, I'll find out what is a relevant event. And I know that if I know what is a relevant event, then I can say that the probability X is taking the value 2 is the probability of this event, which I already know, which is 1 by 36. Similarly, probability X is taking the value 3 is the probability of this event happening, which is 2 by 36, and so forth. Is that clear? So if I want to assign probabilities of X taking a particular value, I find out what is the corresponding event. So I can assign probability. So I know X takes, so this is exhaustive. I know X takes value 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And for each of these values, I identify what is the relevant event. Similarly and I know what is the probability of the relevant event. So I get what I refer to as the probability distribution of my random variable. Let's look at Y. Now, same thing I can do with Y. I know what are the relevant events. Now, what is the probability Y equal to 1? Is the probability of this event. What is the probability of that event?
11 by 36.
11 by 36.
7 by 36. Similarly, the probability of this event is 1, 2, 3, 4, 5, 6, 7, 8, 9.
9 by 36.
Okay. So I can, so the summary is for every random variable I'm defining on the sample space, I can find out what is the relevant event and I can assign what are called probabilities. Okay. So now the question is, I can broadly, just as whenever I talked about a natural variable, forget about random variable. When we talked about data, we said that we can broadly, and especially numerical data, we said that, remember, when I have data or my variables, I had two types. One was what I call categorical and one was what I said numerical, right? Within numerical, I had again divided it into discrete and continuous. Remember this?
Yes,
Yeah.
ma'am.
Yeah.
Yes, ma'am.
Now we are not interested in categorical because our variable here is assigned to a numerical value, right? We are not assigning any categorical value to this variable. So we are only assigning a numerical value. So I am only interested in numerical random variables. Agreed? Now within numerical random variables, I have a random variable which takes discrete values or continuous values, a random variable that can take at most countable. So again, remember, whenever I refer to a discrete variable or a discrete random variable, I can count the values this random variable takes. Whenever I have something associated with a count, I say it is discrete. However, when the outcomes are numerical but cannot be counted and are infinitely indivisible, so I measure here. So whenever I can count, it is a discrete random variable. Whenever I can measure, it is a continuous random variable. So let's go back. If I'm counting the number of accidents that happen in a intersection during a period of time, will that be a discrete or will that be a continuous variable?
Discrete.
Discrete.
If I'm counting the number of white balls in a bag having 15 white and
Discrete.
25,
Discrete.
again it is discrete.
Discrete.
If I'm looking, if X is the height of an individual I'm picking up at random, am I counting the height or am I measuring the height?
Continuous, ma'am.
Continuous.
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 The time taken for a bulb to last?
Continuous.
Continuous.
Okay.
Continuous, ma'am.
The time taken is
Yes, ma'am.
continuous. If I'm looking at the weight or measuring the weight, again it is
Continuous.
Continuous.
clear. Okay. Demand, sales, all of this
Continuous.
continuous. Okay, because it depends. You don't count the demand, right? You measure the demand. Okay, so that is the first understanding. Is we will be looking at discrete and continuous random variable. So let's focus first on discrete random variable. Okay, so in discrete random variable, it takes one of the possible values. So it basically it makes sense when I am talking about x equal to some value. That is when I'm talking about discrete. Whereas in a continuous value, it will not take a particular value, but it will take a set of values that forms an interval. So I say x belongs to an interval. So this is discrete and this is continuous. Is that clear? When I say x belongs to an interval, it is continuous. But when I say x takes a value, I say it is discrete. So the first thing that we need to understand is, again, number of accidents, number of spelling mistake, number of times a person takes a particular test before qualifying. All of these are discrete. The temperature of a person, you measure temperature, you don't count temperature. Height, speed, you don't count the speed, you measure the speed. Again, the time taken by a person to write an exam, time is also measured. So these are typical examples of discrete and continuous variables. Now we are going to look at these discrete and continuous variables from a random variable perspective. So first let's focus on a discrete random variable. Again, recall when I talk about a discrete random variable, I have a variable x which takes x1, x2, x3. It is taking n specific values. So here I'm assuming it's taking countable and finitely number of values. Okay, so that's why I'm putting x1, x2, x3 up to xn. For example, again, let's go back. I'm counting the number of heads in my tosses of a coin. Yes, Danya?
Ma'am, here x1, x2, and x3 are discrete, right?
The
Or
values
should-
taken.
The value is taken by
x3.
x.
So let me give the example. Okay. So I have x, s is taking x, hh, and my x is taking the, I'm counting the number of heads. So what are the values it is taking? 0, 1, 2, right? So my x1 is a 0, x2 is a 1, and x3 is a 2. Is that clear? So it is taking discrete values. So what is my n here? It is, I have 3. How many discrete values is the random variable taking? 3, right? What is the value of x1? 0, x2 is 1, and x3 is 2. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Similarly, if I'm tossing a rolling a die once and it is taking 1, 2, 3, 4, 5, 6, I define the random variable as the value that is coming up. I can just map 1 to 1, 2 to 2, 3 to 3, and 6 to 6, right? So what is n here? It is 6. X1 is taking the value 1, 2, 3, 4, 5, and 6. Is that clear?
Yes,
Yeah.
Yes,
ma'am.
ma'am.
Now, this is when I have finitely number of values. It is taking exactly 3 values. Okay. Again, silver spray, whoever it is, I am going to only focus on random variables and discrete and continuous distributions. In the interest of everybody else, this is a revision section only for those topics. Okay. Right. So Aryan, you're saying if height is measured in centimeter up to 1 decimal point, you don't count height. You yourself have written measured, right? Is that clear?
Yes, ma'am.
You're
Yes, ma'am.
measuring. So it could be 18.1, 18.2 or whatever it is, but you're measuring it. So this height can take a value between 18.1 and 18.2. It could take even 18.15. You're not restricting the value of that height. You're getting it?
Yes, ma'am. Yes, ma'am.
Yeah, so it will not be a discrete random variable. Okay, whereas when I'm counting the number of people, it would be 1, 2. It won't be 1.5 people, right? X cannot take a value between 1 and 2. You get the difference?
Yes, ma'am.
Okay. Now, so here is everybody clear with x1, x2, x3 and all of that? The values it is taking?
Yes,
Right.
Yes,
Yes,
ma'am.
So I'm, yeah?
Yes, ma'am.
Yes, any measurement is continuous, right? Okay. Now, if I repeat the experiment, let's look at this. A person, number of times a person takes a particular test before qualifying. What is the sample space of this?
1, 2, 3, 4.
It can be 1. The person can take 1. The first time qualifies in the first time. Can take 2. Okay. What are the values this can take? The random variable.
Discrete.
Discrete. And what is it? What are the values? It's 1, 2, 3, so forth, right? So if I write it in terms of x1, x2, x3, this is, so x1 is 1, x2 is 2, x3 is 3, and it can take any value, infinitely many, but countable.
Natural.
Yes, ma'am.
Yes, ma'am.
Yes, right? And
Yes.
see, we start the session at 8 o'clock. Whatever topics are going to be covered in the session was already told at 8 o'clock. Okay. So I'll repeat only once more. It is random variables, discrete and continuous distributions. Okay. Right. So you can see that. So I can typically, so if I take x1, x2, xn, so you can represent it in a tabular form. What is this P of x1? Associated with every value this random variable is taking, I have a probability that x takes that value.
Yes, ma'am.
Right?
Yes.
So this, so with, if x is taking the value x1, I have P of x1, which is nothing but probability x takes the value x1. This is probability x takes the value x2. This is probability x takes the value x3. And this is what we refer to as the probability mass function. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Now,
ma'am.
what are the properties of this probability mass function or probability distribution function? Okay, because it is telling me what is the distribution of this random variable x. What is the probability with which x takes the value 0? So if I have this, again, go back to tossing our coin, x takes the value 0, 1, 2. What is the probability with which it takes the value 0?
Px1.
1 by 4. ma'am.
1 by 4. This is 2 by 4. This is again 1 by 4. So this is what we refer to as the probability mass function. What are the properties of it? Because it's a probability, obviously it has to be greater or equal to 0. And it is equal to 0 and it should add up to 1. So what does it add up to? This adds up to 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
This is what we refer to as the
Yes,
probability mass function. Now, when I have the probability mass function, I can talk about a graph of a probability mass function because I know x takes discrete values x1, x2, x3 with the respective probabilities p of x1, p of x2, p of x3. And I know this probability lies between 0 or 1. So for any value, it is taking x1, x2, x3, I can graph this. And this is what is called the graph of the probability mass function. For example, on the screens, you can see that x is a random variable, which is taking 4 values, 1, 2, 3, 4. And I have graphed it. Probability x equal to 1 is 0.4. First of all, is it a probability mass function? Yes, because probability of xi is greater or equal to 0 for all xi. And it adds up to 1. And you can see this is a right skewed distribution. So that's why it is also referred to as a probability distribution function, because it is telling you how this random variable, what is the graph of the distribution. This is right skewed. On the other hand, you can see that this is a left skewed distribution. And you can see that I can talk about a symmetric. If it were 0.1, what would have been the shape of the distribution had it been 0.1, 0.2, 0.3, 0.2, 0.3, 0.3, and 0.2? What would have been the shape of this distribution?
Symmetric.
Symmetric. First of all, is that a PMF or probability mass function?
Yes, ma'am.
Yes, ma'am.
It adds up to 1. Okay. On the other hand, when I have a discrete distribution or the continuous distribution, I don't have a probability mass function because I'm not talking about x taking a value. Rather than I'm saying x belongs to an interval. That's what we said. X does not take a particular value, but I can say that x belongs to an interval. So the minute I say x belongs to an interval, I don't have a probability mass function. I have what is called a probability density function. Is that clear? The equivalence. I am saying that
Yes.
probability x belongs to that interval is nothing but the definite integral between a and b f of x dx, which is nothing but the area under the curve between a and b. We know the definite integrals are expressed as areas under the curve.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So rather than talking about this, I'm looking, that's what it is. Okay, this is what is right skewed and left skewed. I think we have already done about skewness when we talk about descriptive statistics. Okay, so this is what we say is a probability density function. Again, just as I wanted P of x equal to xi should be greater than 0 and summation probability x equal to xi is equal to 1, I have f of x is greater or equal to 0, and I need that over the entire interval it is defined. Okay, I need the area to be equal to 1. Over the entire area, it should be equal to 1. Is that clear? This is what we refer to as
Yes,
a
ma'am.
probability density function. So when I have a discrete random variable, I have a probability mass function. When I have a continuous random variable, I have a probability density function. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So the next thing is, so the so when we refer to as a, so conventionally, because I only talk about a continuous variable lying in an interval, conventionally the probability x takes a value if x is continuous is defined to be 0 because it does not take a particular value. It only belongs to an interval. Is this clear? This concept is very important. Hence, if I'm mentioning a is less than or equal to x is less than b, is same as probability a is less than x is less than b, because x equal to a is always equal to 0. It's equal to 0. So these two are equivalent. So far, so good.
Ma'am,
Yes,
could you
ma'am.
please repeat
Please
this?
explain again. Yes, ma'am.
See, when I'm having continuous, see, first of all, I have discrete and I have continuous, right? Discrete, I'm saying x is taking a particular value. That's what I say, x equal to a value. Whereas continuous, I say x belongs to an interval.
Yes.
When I'm talking about x belongs to an interval, let me call that interval a to b. Okay. So when I only can define x's in an interval. So when I'm talking about the probability also, I say probability x belongs to this interval. That's what I mean by a is less than x is less than or equal to b.
Yes, ma'am.
Yeah.
So ma'am, A and B are included or not? Like,
Yes, ma'am.
yes. So that's what I'm saying. The chance that x is equal to a when x is a continuous random variable, this is actually, I cannot define it. So I'm taking x, taking a particular value. If x is continuous, I'm saying it's equal to 0.
okay.
So if a is less than or equal to x is less than or equal to b, since x equal, it's same as probability x is a is less than x is less than b. It's the same thing. It belongs, whether it is in this interval or this interval, it's the same, because probability of x, it is between a and b, or a and b are included. It doesn't make a big difference when I'm talking about continuous random variables, because it is an entire interval, right? 2 to 5,
Yes, ma'am, got it.
probability x is that clear? I'm
Yes,
not
ma'am.
talking about x is
Yes,
exactly
ma'am.
taking a value 2.
Yes, ma'am.
Whereas when I'm
Ma'am.
talking about a discrete random variable, it takes exactly these values, x equal to 2, x equal to 3, x equal to 4, and all of that. Is that clear?
Yes, ma'am.
Okay. So
Ma'am.
the next concept is,
Ma'am.
yeah,
But it makes some difference now in value.
what value?
Both side LHS.
No, it doesn't make any difference. Because you're
Okay.
integrating from some point to that a, right? and it is
Yes, ma'am.
continuous. See, when you'll understand that very soon. So when I'm talking about a cumulative distribution function, I know that this x is taking values x1, x2, x3. I assume x1 is less than x2 is less than x3. Okay. So in other words, I know this x is taking some value x1, x2, x3. I define this function f for all the values on the real line to 0, 1. Let me explain what we are trying to do. For example, if x is taking value x1, x2, x3, and x4, x1 is less than x2 is less than x3 and x4. Okay. What is the and I have defined this probability of what is probability x is equal to 0? Outside this
0.
interval, it is taking the value 0 for everything
0.
else.
Yes,
Right.
0.
So now what would be probability x equal to -1?
0.
0.
Also 0.
So here it makes sense for me to ask probability x is strictly less than 1.
Is 0.
It is going to be 0 for all of
Yes,
A
ma'am.
that is less than 1, it will remain 0.
Yes.
Yes.
So when I'm taking, so this is still 1. Till this point, it is going to remain 0. So let me open the white ball. 1 second. Are you all able to see a whiteboard also?
Yes,
ma'am.
Yes,
Yes,
ma'am.
ma'am.
Right? Yeah. So now you look at it. This is my 1, this is my 2, this is 3. Okay. So if I look at this thing, till I hit this point 1, it is going, if this is my f of A, till I hit 1, it is going to remain 0.
Yes.
At 1, it is taking the value 1/4, right?
Yes, ma'am. Yes.
And it is going to remain at 1/4 till it hits 2, right?
Yes, ma'am.
Yes, ma'am.
Yes.
Because f of what is probability x equal to 1.1?
1/4.
1/4.
1/4.
Equal to 1.1. Probability x equal to 1.1.
0.
This is 0, right? But what is probability x is less than or equal to 1.1? It is probability
1/4.
x equal to 1 plus all of that, right? So it will remain at 0. Is that clear?
Yes, ma'am.
Yes, ma'am.
So the minute
Yes,
it
ma'am.
hits 2, this is going to be 1/4 plus. So you can see that it would be 1/4. The minute it hits 2, what is the probability here? It is. So you can see that this is how my this one, these points are what we say are the points of discontinuity. Is that clear?
Ma'am, I'm sorry to
For when the
how come 1.1 became 0? Because 1.1 is after 1, no? Because
Yeah.
at 1 the probability became
Probability x equal to 1.1. I've not defined that, right?
okay, it's not defined, that is why. Okay.
It is only for x equal to 1, it is 1/4. X equal to 2, it is 1/2. X equal to 3 is 1/8. 4 equal to 1/8. This is how I've only defined a probability for 1, 2, 3, 4. For everything else, the probability is equal to 0, right?
Okay.
Yes, ma'am.
Okay, ma'am.
Okay. So when I'm looking at the cumulative distribution function, till this point, it is going to be 0. At this point, it will become 1/4. At this point, it will be 1/4 plus 1/2, which is 3/4. At this point, it will become 7/8, and then it's going to be 1, and it continues to be 1. Is that clear?
Yes, ma'am.
Yes, ma'am. Yes.
Yes, ma'am.
Because what is happening, the whole idea is, this is what is, 1 second, let me. Yes. Okay, so this is what I have plotted is the cumulative distribution function. The reason it is called cumulative is I am adding all the what is probability x is less than or equal to A? It is probability x equal to A plus all the probabilities of x is less, probability x is less than or equal to 1. It's only probability x equal to 1, right? I don't have anything else. Probability x is less than or equal to 2 is probability x equal to 1 plus probability x equal to 2. Agreed? X
Yes,
is
ma'am.
less than
Yes,
or equal
ma'am.
to 3 is
Yes, ma'am.
probability
Yes,
X equal
yes.
to 1 plus X equal to 2 plus X equal. I am cumulating it. Okay, so this is, I'll get a step function if it is a discrete random variable. On the other hand, if I have a continuous random variable, I have to, so what is probability X is less than or equal to A? That would be minus infinity to A, f of X dx. Agreed?
Yes, ma'am.
Okay, so it
Yes,
is an
ma'am.
integral.
Ma'am, the probability of X is less than or equal to A is something from the beginning to probability of X is equal to A for discrete random variable.
Yes, for continuous also. So let's look at a random variable of this kind. Okay, we'll be defining it again when we'll be looking at specific random variables. But you can see for a continuous random variable, it's minus infinity to A f of X dx. Right? So I can define, suppose this is my random variable. Okay, and this entire area is 1. If I'm looking at C, if I want f of X equal to C, it is this integral between minus infinity to this point. So it is this area.
Yes.
Now if I have f of X is less than or equal to C2, it would be this entire area.
Yes.
Yes, ma'am.
F of X is C3, it's going to be this area.
Ma'am,
If I have a D1 here, what is f of D1?
0.
It is 0. If I have an E1 here, what is f of E1?
0.
0.
F of E1. This is
1.
minus
Ma'am,
infinity to
1.
E1. So it would be
1.
1, right?
1, ma'am.
You get it? What would be F1? It would be this area. This entire area. Is that clear?
Yes,
Yes,
ma'am.
Sir, when I'm talking about a continuous random variable, I'll not have, so till this A or this point, let me call it capital A, it will again remain 0, then it will keep increasing and then it will again taper off at 1. So there are no discontinuities. That's what I want you to see. Is it clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Azad,
Ma'am,
you have a
ma'am,
question?
I have a doubt. Like,
Yeah.
if the interval is mentioned, A to B is already mentioned, then why are we starting from minus infinity?
Because this A to B is the definition. So I have defined my density function between A and B. Okay. But this cumulative distribution function is defined for every real value. If you go back to the definition of cumulative distribution function, it is defined for every real value of A. Okay. So it is defined outside the range also. I'll have an f of X outside the range of definition and after the range also. So it will be 0 here and here it will take the value 1. Is it clear?
So from minus infinity to A, it is 0, but still we are considering it since it is
Yeah,
defined.
it is defined as 0. I can have a function which is taking a value 0, right? So
Yes, ma'am.
when I have a continuous, suppose I've defined only A to B, till this point it will be 0. Between A and B, it would be like this, and after B, it will remain 1.
Yes, ma'am.
Is that clear?
Yes, ma'am.
Yeah.
Yeah.
So that is what it's a cumulative distribution function is defined for every real value. Is this clear?
Yes, ma'am.
So that's why I said it is a function which maps every point in the real line to 0, 1. It will take only the value between 0 and 1. After, it is not taking any other value. You see, it's either taking 0, it is taking up to 1, and then it is remaining at 1. Similarly, you look at this, it is 0, and after this point, it will remain at 1. So it takes values between 0 and 1. Is this clear?
Yes, ma'am.
Okay. So what are the concepts that you have learned? You have learned about a random variable, the definition of a random variable, the concept of a probability distribution function, which is a probability mass function if it is discrete, probability density function if it is continuous, and the concept of a cumulative distribution function. Any questions so far?
No, ma'am.
No.
No, ma'am.
No, ma'am.
Okay. So the next
Ma'am, I have a question.
Yeah.
Ma'am.
Yeah, please.
In some probability table, they f of x is equal to 0 also have the value, means we toss coin thrice, there will we take probability of heads, and x is equal to 0 means there is no heads. But there that tail is a uh, one event that occurs, that probability will 1 upon 8 na.
Where? Can you ask a question with respect to this example?
Yes.
Yeah, please tell me.
So we take a example, coin toss thrice, and the probability table is x is equal to 0 means the event is only heads.
Okay.
There are heads, so x is equal to 0 means there is no head.
X equal to 0 is?
There is no head, only tails.
Okay.
And
okay.
that
So x is equal to 0 is 1 by 4. 1
yes.
is 2 by 4. 2 is 3 by 4. Yeah. So what is your question?
No, x is equal to 0 is 1 upon 8.
Why? For you're tossing a coin twice. Thrice.
Thrice.
1
Yes.
upon 8. Then this is 3
Yes.
upon 8. 3 upon 8. And again 3 is 1 upon 8. Okay.
Yes.
What is your question?
So I am telling that sometimes f of x is equal to 0 also be a probability.
Yeah. So here what happens is your f of 0, okay, would be 1 by 8. So till less than 0, it's going to be 0. At f of 0, it'll be 1 by 8. At f of 1 would be the 4 by 8. Then it would be 7 by 8. And then it will be 1 by 8.
Yes.
For a less than 0, it would be 0. Okay. 0 is less than a is less than 1. It would be 1 by 8. So same thing would happen.
Yes.
Okay. Yeah.
I just had one doubt. Even
Yeah.
from the cumulative distribution function is to be considered from the probability mass function.
Probability mass function gives you what is the probability x is taking a value. Probability cumulative distribution function is probability x is less than or equal to that value. Provided that value this one, x1 is less than x2 is less than x3 because it is ordered. Is that clear?
Yes.
Okay, right. So the next concept is what is called the expectation of a random variable. Now, why do we care about expectation? And this is again, I'll go back to the game that we told that I'm rolling a dice. I have the outcome is 1, 2, 3, 4, 5, and 6. If I get an odd number, I give 10 rupees. Okay, I'll give away the value. So let me tell what is my payoff. Okay, if I give an odd number, I give -1, -3, -5. I'm giving away money. But if it's an even number, I get 2, 4, and 6. I'll repeat the game. I roll a die. Okay, if an odd number comes, I give money to the opponent. 2 people are playing this game. Okay, if an even number comes, the opponent gives me the money. The question is, will you play the game? How will you decide whether, because it's gambling? Yes or no?
Yes, ma'am. Yes, ma'am.
Will you play the
Ma'am,
game?
we'll check the result in long run.
You'll check the?
We'll check the result in long run, like average value in the long run.
So that is what. So you'll check for the what would happen in the long run. That is, if I repeat the game sufficiently long number of times, then what would happen? That is what we refer to as the long run average. And that is what we get as an expectation. So I know this is going to be the value of my payoff, 1 by 6, 1 by 6, 1 by 6, 1 by 6. I compute what is called expectation of that random variable. And this expectation is a long run. Actually, it is a long run average. For example, if I had just taken 1, 2, 3, 4, 5, and 6 with probability 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6, I know that the expectation of X is going to be 3.5. Now, this expectation of X does not mean that if I keep tossing a die or rolling a die, I'll get one of my answers will be 3.5. I'll never get 3.5 because the die can take only value 1, 2, 3, 4, 5, 6. But it says that on an average, the long run average of the values I get would be 3.5. Just let me take a minute to read the question. If a discrete random variable is defined, X equal to 0, 1, 2, 3, then yeah, see, but what I said is, yes. So, Nadwara, you're saying X takes the value 0, 1, 2, 3. What is probability X is equal to 5? It is 0. But what is probability X is less than or equal to 5? It will be probability X equal to 0 plus X equal to 1 plus X equal to 2 plus X equal to 3, which is equal to 1. So, that's why I said it will take the value 1 for all values greater than 3. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes,
Yeah.
ma'am.
Okay. So X equal to 5 would be 0, but less than or equal to 5, it will be always 1. Okay.
Okay.
Excuse me, ma'am.
Yeah.
Ma'am,
Yeah, please ask.
ma'am, I had a doubt. Ma'am, the expected value is like 3.5. So this is showing the expected value in a long run. Long run means like many a times if we do the experiment, then.
See, many a times, if you, that doesn't mean that you're going to roll a die many a times. Okay. It says that, see, the notion of the expectation can be considered or can be interpreted as a long run average, because eventually, how are you getting this 1/6, 1/6, 1/6? You're getting a probability also. If you're taking a dice experiment, okay, you try and do this on your own. You roll a die 100 times, note down what is the frequency distribution. This is something which we did even in the class. You can see that, okay?
Yes.
Do it 1,000 times, do it 10,000 times. You see that as my number of times I repeat that experiment. What is the experiment? Rolling a die. This converges to 1/6, 1/6, 1/6. This is something which you have seen. It converges to the probability of it taking. So I can define the notion of an expectation as a long run average. But I can compute it just by doing xi, probability x equal to xi. That doesn't mean I'm going to roll a die 10,000 times or 1,000,000 times. This is the theoretical definition. Is that clear?
Yes, ma'am, it is clear.
The way I interpret it is as a long run average. Is that
Yes,
clear?
ma'am.
That's why I can expect it to happen. Okay. Right. So similar to what we have defined, we can always represent the expected value as a Greek alphabet mu. The variance is expectation of x minus mu whole square. And I have a computational formula, which is nothing but expectation of x square minus x mu square. This is the way, it's a computational formula to compute the variance of x. So given any random variable, okay, we need to find out what is the expectation of that random variable and variance of that random variable. Expectation is given by mu, variance is given by sigma, and these are referred to as the parameters of the distribution. Sometimes this is what we are getting. What is the mean of the distribution and the variance of the distribution? Is that clear?
Yes, ma'am.
Yeah. So any questions so far? Because now we are going to go to look at specific distributions. Okay.
What is mu here? Actually, these are also parameters.
It is denoted, expected value of a random variable is denoted by the Greek alphabet mu. It just convention. Okay. Expectation or the long run average, I give it as mu, and variance is sigma square. Okay.
Is this a mean?
In a sense, okay, the long run average. So I'm just telling it is mean. Okay. Is that clear?
Yes, ma'am. Yes, ma'am.
Excuse me, ma'am.
Yeah.
Ma'am, I have a small doubt in cumulative frequency, the graph of cumulative frequency. Can I ask that?
Yeah. This one?
Yes, ma'am. Yes, ma'am. Ma'am, here in the vertical lines, the joining the part, it is simplifying
It is
something.
not joining. It is not joining. It is not joining. This is showing the discontinuity. See what is happening till this point. It has been 0. Okay. At this
Yes, ma'am.
point, it is taking the value 1/4. It is continuing to be at 1/4 at 2. At 2, it is jumping to this point. So what is happening is there is a discontinuity between less than 2 minus some very small epsilon to 2. Okay. That is why it is discontinuous at that point. This is not continuous. Okay. It is, you can actually, the graph is like this. Is that
Yes,
clear?
ma'am. Got it. Yes, ma'am. Got it.
And
Got
then
it?
the difference of the step gives
This
the
is only
probability.
showing the discontinuity. That's why it is not joining them. This is how it is till this
Ma'am,
point.
so the interval of discontinuity will be between 2 and 3. The sorry.
No, not between 2 and 3. This is 1. Okay, this is 1. This is 2. It is continuous between 1 and 2. Between less than, very much less than 2 and 2. It is the discontinuity is between till less than 2 minus some delta to 2. That's it. That it is not an interval of discontinuity. It's just very, very narrow point. At 2, it is discontinuous.
Okay. Yeah. Got it.
And ma'am,
yeah,
this step gives us probability, na? The difference of step.
It gives you, yeah, it is
Probability.
because I define f of a to be a probability x is less than or equal to a. That's why it takes values only between 0 and 1. Is that your question?
Yes, ma'am.
It is a probability function. This is for a discrete. I have set points of discontinuity. Whereas continuous, if it's a continuous random variable between a and b, it would be like this. This would be my shape of the distribution function. It is increasing, monotonically increasing function. I cannot have a distribution function which is like this. Because f of this one would be adding up, right? It is accumulating. It will only add. It can never come down, right?
Yes, ma'am.
Is that clear? So it is an increasing, it's a non-decreasing function. Okay. Is that clear?
Yes, ma'am.
Okay. So now, if there are no doubts, we will go and look at specific discrete distribution. So if you look at what we are going to look at, so this is the first part, which was random variable, the probability mass function, density function, cumulative, expectation, and variance. I hope at a conceptual level, everybody is clear about it.
Excuse me, ma'am.
Yeah.
Ma'am, I am still confused that, like, in expectation, in the example that you gave of rolling a dice, the value is 3.5. So, ma'am, does that mean that in the long run we'll get 3.5 as the outcome of rolling a dice?
No, that is what I'm saying. In the long run, you'll not get 3.5. This 3.5 is the mean of the outcomes. Okay.
Okay, ma'am.
It does not mean that in the long run you're going to see. For example, if I'm having tossing a coin, okay, what are the outcomes?
So, ma'am, is it the
head and tail? Let me complete this. So, if I assign a 1 to a head and 0 to a tail, okay, what is the expectation of x?
1/2.
It's just 1/2, right? So does
Yes,
this
ma'am.
mean that I'm going to get something between head and tail? Because head is 1 and tail is 0.
No,
ma'am.
No. So the value on it, that is what it means by an expectation. Yeah, there was some other question.
Is it the 3.5 mean of the?
It is, see, in a sense, x is taking the value 1, 2, 3, 4, 5, 6, right? The mean of these values. In a long run, that would be the expectation of the values taken. It doesn't mean that I'm going to get a 3.5. Okay. Whereas suppose I'm saying about the payoff, right? If you get a 1, you get a 10. If you get or suppose I say it's a payoff 3, 4, 5, 6. The average payoff is about 3.5. That is something, it makes sense. It depends on what you're talking about, right?
Yes, ma'am.
Yeah. Yeah, there was some other question.
Ma'am, can you tell the physical importance of variance, means other than that, if variability of some two data are given, if variance of some data is 0.5 and 0.3, then we know that first data has more variability. But other
Yes.
than that, can we tell anything about if that data has two random values, 0 and 1, then can we say that probability of this is somewhat difference, like 0.2 or 0.3? Can we say something like that?
See, the notion of variance is the same thing. See, for example, if I take a random variable, x is taking the value 0 and 1, okay, with probability half and half, okay, or -1 and 1. Can I define something of this kind?
Yes, ma'am.
What is the expectation of this random variable?
0.
It is 0, okay. Does it have a variability?
Yes, ma'am.
What is the variance?
No.
On the other hand, suppose I have a random variable taking a value 1 with probability 1. What is the expectation of y?
1.
Or it is taking the value 1. It is taking the value 0 with probability half and 1 with probability half. What is the expectation of y?
1 by 2.
1 by 2. Both of them. So suppose I'm having a random variable. So say x is taking the value
It is
minus.
following the Bernoulli trial.
Pardon?
Following
this
the
is a Bernoulli trial.
trial.
Yeah. Bernoulli trial if you're mapping it to 0 and 1. Okay. Right.
Yes,
So the
ma'am.
idea is, see, just as why did we need the concept of a measure of dispersion when we had measures of central tendency? Why did we need the concept of measure of dispersion? Because central tendency did not capture the entire thing. And the example that we always say is, what is the mean of 1, 2, 3, 4, 5?
15.
3, right? Mean, average of 1, 2, 3, 4, 5. What is the average of 3, 3, 3, 3, 3? Okay, so the idea is, see, sometimes the expectation alone is not enough, right? Because the expectation, the distribution, finally we are interested in distribution. So suppose this is the marks obtained by students in section 1 and this is in section 2. Both of them have the same average. So just because the average of marks obtained by section 1 and section 2 are the same, is it right for me to say that section 1 and section 2 have the same behavior?
No.
No, ma'am.
Why not?
Because distribution is quite different among the
Because I can say that
classes.
section 2, I see a lot of consistency. The variability is almost 0. Everybody performing the same. Whereas section 1, I have some people who are performing badly and some people are performing very well. Right? So there is a variability. So that's the same reason, because the mean does not capture this dispersion, we need a measure of dispersion, and variance does that. Does that answer your question?
Yes.
Yeah. So that's the same thing. Only thing, now we are talking about random variables and the value it is taking. So I need a measure of dispersion or measure of spread in addition to measure of central tendency. Okay. So the simplest of the random variables is what we call a Bernoulli random variable. Here a Bernoulli random variable, we say that it takes two values and I'm going to map that to 0 or 1. It is again, this is convention. It is not necessary that I always map to 0 or 1. It could be any two values, but I'm just, for ease of understanding, I map it to 0 or 1, where 0 could be mapped to a failure and 1 could be mapped to a success. So any experiment wherein I can talk about a failure and a success, and the probability of the failure is, success is P and failure is 1 minus P, I call it a Bernoulli random variable. Remember, it does not mean that my experiment has only two outcomes. For example, if I roll a die, how many outcomes do I have?
6.
But I can define a Bernoulli random variable. I can define a success to be the coming of an even number and an odd number. So this is the Bernoulli random variable takes two values where I'm mapping a failure to a 0 and success to 1. The probability of a success is P. So the probability of failure is going to be 1 minus P because I have only two variables. In that case, the expectation of a Bernoulli random variable is 0 into 1 minus P plus P, which is P. And the variance is going to be P into 1 minus P. So variance expectation of X square is also going to be P. So my variance of X is P minus P square, which is P into 1 minus P. Now this one again, roll of a die, I can talk about it as a discrete uniform random variable, because if I'm going to map this probability mass function, I have equal lengths of bars of equal height. So this is a discrete uniform random variable. Again, the expectation is n plus 1 by 2. I can compute what is the variance. Now let's look at what we mean by identical and independent and identically distributed Bernoulli trials.
Ma'am, your voice is breaking in between.
Now is it okay?
Yes, ma'am.
Okay. Is it fine now?
Yes.
Yeah. Okay. So now suppose I'm again tossing a coin. Is the whatever is happening in the second toss, does that depend on what was happening in the first toss?
No.
No.
Independent. Similarly, the probability of success in the second toss, is it the same as the probability of success in the first toss?
Yes. No.
It is. So
No,
they
ma'am.
are identically distributed, because I cannot say that the first toss has a probability of success which is 0.5, second toss will be 0.4. No. So I call these trials, when I'm tossing a coin twice, to be identical and independently distributed. And each one of them is a Bernoulli trial. Okay. For example, where are these Bernoulli trials independent and identically distributed? I go to a shop. Okay. And I say that the probability of a customer making a purchase is 0.4. Probability of any customer making a purchase is 0.4. Now the probability of me making a purchase, is it independent of the probability of customer 2 making a purchase?
Yes, ma'am.
Yes, ma'am.
It is independent. If I have a probability of making a purchase which is 0.4, what is the probability of that other customer making a purchase?
It is independent.
That's also 0.4 because it is identically. So this is an independent and identically distributed two Bernoulli trials. So I can talk about the same thing about 50 people. All of them are independent and identically distributed. I'll have 50 Bernoulli trials.
Yes.
Yes.
Right?
Yes, ma'am.
So when I have independent and so if I have n independent trials such that each one of them is a success. So here I can define in this shop example, I can define success to be making a purchase. And what did I say was the probability of that success? I said it was 0.4. Okay. So what is a failure here? Not making a purchase?
0.6.
And if there are 50 people, I have 50 independent trials. Okay. So, and if X is counting the number of people who are making a purchase, what are the possible values this X can take? In a day, I have 50 people, and X is the number of people who are making a purchase. What are the values?
1 to 50.
0 to 50.
0 to 50, ma'am.
Or 1 to 50?
0 to 50.
0 to 50, right? That's the possible values. Okay. Independent and identically distributed is the same as mutually exclusive and collective. No, it is not the same. Okay. Because when you're talking about a probability mass function, it is collectively exhaustive. You're already looking at everything. IID is independent and identically distributed. Already I have said that mutual exclusiveness and independence are not the same. Mutual exclusiveness is disjoint events. Independent events are different. Okay. Is it clear?
Yes, ma'am.
Yes, ma'am.
X is taking the value 0 to 50. So I might want to know what is the chance if I'm the shopkeeper and X is the number of people making a purchase. I want to know what is the probability X equal to 25. What does this translate to? What is the chance that 25 people have made a purchase? Is this a good information for me to have or not?
Yes. Be an average.
Right. So
Yes,
first
ma'am.
thing is we understand, given the situation, I see that this X can be modeled as independent. I'll have that 50 people. I see that it is an identical and independently distributed Bernoulli trial. And I say that this X follows a binomial distribution. So I have N independent and identically distributed Bernoulli trials. What are the values it takes? It takes, what is the N in my example? It was 50. Okay, right. P is the probability of success. So this P, what did I define success here? Making a purchase. My P here was 0.4. N was 50, and I'm interested in number of successes, probability, number of people who made us purchase. So what are the values this takes? It takes the values 0 to 50. What is the probability? What does this mean? The outcome SSSSS, what does that translate to?
All the successes.
All the people make the purchase, right? And that is, since it is, what is the chance with which person 1 makes a purchase? 0.4 into 0.4, 0.4 to the power of 50, which is P to the power of N. Okay, so you can see that this is how we have all the, so I have totally, these are the number of outcomes and these are the probabilities. Okay, and with this probability, you can see that the Bernoulli random variable, I can say that the probability of I success in N trials is given by N choose I. Why is it N choose I? If you look at these probabilities, okay, SSS, FS, okay, SSS, FSS. So only one failure, this failure can, I have N points. How many ways I can choose this failure in N places? It can be either the last one or the last but one or the last but two or up to the first point, right? Is that clear?
Yes, ma'am.
And that can happen in N choose 1 ways.
Yes, ma'am.
How many ways can I put 2 failures in N places?
NC2.
How many ways can I put R failures in N places? N choose R. So this N choose I comes from that. I successes in N places, P to the I into 1 minus P to N minus I. So this is what I refer to as the probability mass function of a binomial distribution. Is this clear?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, this is the binomial distribution. And again, if it is right skewed and left skewed, we can see, you can see this binomial distribution where P is 0.3. It is the skewness, you can see if P is 0.5, it is symmetric. If it is P is 0.8, P is greater than 0.5, I get a left skewed distribution. Okay. However, if N keeps increasing, okay, even if P is 0.3 or 0.8, you can see that the distribution looks symmetric, appears to be symmetric. Okay, as N keeps increasing. See, when N was 4, you can see the skewness. But as N keeps increasing, you can see that the skewness is somehow reducing. Can you see that? It's becoming more symmetric. It is approaching symmetry. Yeah.
Yes,
For
ma'am.
large N,
Yes,
this
ma'am.
binomial is approaching symmetry. So if you all have already, so this is something which you will see when you are doing inferential statistics, this idea would start playing.
Ma'am,
yeah.
Means we will directly, what will be then answer for large N? Like, because in the slides, I can see it's written left skewed or right skewed.
Yeah,
it's
it
not
is
written like kind of.
It is, no, what I want you to notice here is, it is left skewed, but it is not as prominent as for lesser N, right?
Yes.
As N keeps increasing, the skewness is, you can see that it is almost becoming symmetric.
Yeah.
And it is having some particular shape.
But
right, that is what I wanted to know.
Yes,
It
ma'am.
approaches symmetry. For large N, the binomial distribution approaches symmetry. It is no longer skewed. That's what I wanted to tell.
But when n is also large and p is greater than 0.5, then it goes to right. And when p is less
it is
than,
going to the right because your mean would be, what would be the mean here? It would be 32, right? N into p.
yes, ma'am. That's why it is going there.
So it is shifting. The mean is shifting. Okay, but what I want you to notice is it is becoming symmetric. Is that clear?
Yes, ma'am.
Okay.
Yes.
So the expectation of a binomial random variable is n into p, and the variance is n into p into 1 minus p. I think the derivation, I'm not going to go through it. It is given in your notes, so you can just go check it. So again, this binomial, the most important thing is it has to be identical and independent. That is very, very important. Now, what happens when this loses? So suppose the trials are not independent. So let's look at this experiment which is on your screen. I have 4 white balls and 3 black balls to start with. I'm picking up one ball at a random. What is the chance with which I get a black ball in my first trial?
3/7.
3/7. I'm not replacing the ball. So how many balls do I have if it is a black ball?
Now 2 black balls.
So now in the second trial, what is the chance of me picking up a black ball?
2/6.
So this chance, so are they identical trials?
No, ma'am, they are changing.
So you can see that the probability of success is not the same.
Yes.
So is this a binomial experiment?
Black balls the second.
So it's not
No.
Second.
Pardon? So the chance of you picking up a black ball in the second trial is not the same as you picking up the black ball in the first trial. If your first trial was a black ball, it is 2/6. If it was a white ball, it is 3/6. Right?
This is because there is no replacement.
First trial, and it's also, it is not identically distributed. So this experiment which you see on your screens is not a binomial experiment. Is that clear?
Ma'am, this is only because it is not, there is no replacement, right?
Yes.
If there was replacement, it would have worked.
It would have been identical, correct. Okay, there's no, that's why I said that, but this is nevertheless an experiment. If there was a replacement of the same balls, replacing the same ball, then it would have been a identical. So what would happen here? If it would remain 4W3B, this will also be 4W3B. Again, this would have been the same probabilities, right? If you're replacing it would be 3/7, 3/7. It would be a binomial experiment. But what you see here is not a binomial experiment. Is that clear?
Yes, ma'am.
Yes,
ma'am.
Right. So when you don't have a binomial experiment, okay, so that's when the experiment, so you cannot model it as a binomial distribution. So here you go to what is called a hypergeometric distribution. So the experiment must have changing probabilities of success. Okay. And you can say that you are actually, this one you are looking. So what is a hypergeometric distribution? So here you can see that I have m black balls and n minus m white balls. Totally, I have capital N items. Okay. And I'm randomly selecting n items without replacement. Small n items without replacement. In this, I could have black and white balls, right? Let me call the number of black balls to be small x. So how many white balls will I have? N minus x. Is that clear?
Yes, ma'am.
Now the distribution is number of items of type 1. So I want to know how many black balls do I have in this sample of size n. Okay. So how many ways can I choose small n from capital N?
And choose n ways.
So that would be the total number of ways I can choose small n. That is my number of points in my sample space.
Yes, ma'am.
Right. How many ways can I choose this x from m? M choose x.
Yes, ma'am.
And I can choose n minus x from n minus m. Is n minus m choose n minus x? So the probability of x equal to x is given by this quantity. Is that clear?
Why is it m choose x and not n choose x?
Yes, ma'am, because we are choosing from n. Na?
From where are you choosing these B balls? How many
From M,
black
then.
balls do I
From
have?
M.
From M, right? So that would be M choose X, right? I'm asking, see, for example, if I have, go back here, what is the chance of me having one black ball? Finally. That's what I want to know, right?
1/5.
What is my capital N here and what is my small n here? In this
Capital N would be
experiment.
5. Small n would be 1.
Capital N is 5.
4.
7.
4.
7, man. 7.
man.
Capital
N is 7. 4
M.
plus 3.
What is my capital N? It is 7, right?
Yes.
Yes,
4 plus
ma'am.
3. I have M is 4. Okay. And N minus M is 3. I am picking 2 balls or only 1 ball. Here, finally 2 balls, right? I'm picking up 2 balls, right?
Yes, ma'am.
Yes.
So small n becomes 2.
Now, this could be either a black or a white. It could be a black B1, B2 or a B1, W1, W2 or a W1, B2 or a W1, W2. What is a B1, B2? A black in the first and black in second. Okay,
Yes,
so
ma'am.
my small n is 2. What are the values this black balls can take? It can take 0, 1 or 2. Agreed?
Yes, ma'am.
It is 0 here, it is 1 here, it is 1 here, it is 2 here. So I'm interested in knowing what is the probability x equal to x, where x takes the value 0, 1, 2. Is it clear?
Yes, ma'am.
And this is the hypergeometric distribution.
Explain this again.
Okay, let me explain this. See, I have
Yes,
4,
ma'am,
right?
explain again.
I have 4 black and 3. Let me put it in this case. So this is 4W3B. I have B1, B2, B3, B4, W1, W2, W3. Is this clear? So what is my capital N here?
7.
7.
7.
What is my small m?
4.
4.
What is this? So this is 3.
Yes,
Till
ma'am.
here is it clear? I
Yes,
am picking up
Yes.
2 balls. Okay. From these 7 balls. So what are the possible things I can have? I can have a black and a black and a white and a black. That is a black first one, a black in the second row, black in the first, white in the second, white in the first, black in the second, white in the first, white in the second. Is that right?
Yes, ma'am.
Yes,
Now
ma'am.
I'm counting the number of black balls. X is the number of items of type 1. I'm counting the number of black balls. What are the values this X can take? How many black balls do I have here? How many black balls do I have in this thing?
2.
2 black.
This
1.
1. This is
1.
1. This is 0.
0.
Okay, so I'm asking what is probability x equal to 0. Again, if you look at it, if it were independent, then this is also the same thing. I can think of this as a head and a tail. Right?
Yes.
If it were independent, it would have been a binomial experiment, right?
Yes, ma'am.
The value of x will be 3, right?
No, I'm counting. X can take the value 0, 1 or 2, right?
Yes, ma'am.
Yes,
It can take any of the value, and the probability with which x takes the value 0 is what? Both of them are white, right?
Yes, ma'am.
Yes.
Yes, ma'am.
Both of them are white is this. Right? The probability 4/7 into 3/6. Agreed?
Yes, ma'am.
Probability x is taking the value 2 is 3/7 into 2/6. I just want you all to check it. Is the notion clear? I just want you all to check that it is the same as this. This is the hypergeometric. Is that clear, please?
Yes, ma'am.
Yes,
Yeah?
ma'am.
Yes.
Okay. So in the so you can see x takes the value 0, 1 and 2. Okay.
Yes, ma'am.
With these
Yes, ma'am.
probabilities, you can see that this is the probability. I have worked it out for that problem also. It's 12 by 42, 24 by 42, and 6 by 42, which is precisely what I have here. Okay.
Ma'am, but for one, we have
Yes,
to
ma'am.
consider both the cases, right?
Yes, both the cases. So you can go back here. What are the cases? It is 12 by 42 plus 12 by 42, right? 24 by 42.
Yes, ma'am.
Yeah. Is it clear?
Yes.
So this is 3 by 7 into 2 by 6 by 42. This is 12 by 42. Okay, x equal to 2 is 6 by 42, 12 by 42, and 24 by 42. I'm multiplying. So you again look at what is probability R1 intersection R2. If you recall this is probability R2 given R1 into probability of R1 from my definition of conditional probability.
Yes, ma'am.
Yes, ma'am.
Right. So what is this? So this is probability of a black ball in my second this, given a black ball in my first into probability of black ball. So that is 2 by 6 into 3 by 6 is B1 intersection B2. Agreed? That same thing. I'm using the same logic, right?
Yes, ma'am.
Okay. Okay. So the expectation is n into m by n. So what I want you all to see is as this I can write as n into m by n. What is this m? M is nothing but this, right? N into m by n. In some sense, you can see this variance is also, I can write as n into m by n into 1 minus m by n. Okay. This I can write as 1 minus m by n. I can do that?
Yes, ma'am.
And this I can write as 1 minus n by n into 1 minus 1 by n. I can do that? This.
Yes, ma'am.
Yes.
Now you can see that this m by n is not. So what would happen is if I have identical trial, this, if my m by n is p, this is some np, this is np into 1 minus p. Agreed? If I have, in some sense,
Yes,
if my
ma'am.
n, right? So you can see that the hypergeometric in some ways would actually resemble a binomial distribution when my n is sufficiently large, it is going to be in some sense, it would be, my probabilities would be the same. I would go into the identical space. Okay, that's why, but this is for a hypergeometric. Is that clear? You can see that hypergeometric and binomial for certain values of m and n, they'll have the same distribution. But this is what I wanted you all to see. Is that clear? So the graph of the PMF, again, you can see it is symmetric. For different values, you can see what is happening. Again, here you can see that it is becoming symmetric. Yeah, like a binomial, right? Okay. So the idea is, right, if there are 7 balls, yeah, 6 are red, 1 is black, okay, and you're selecting 2. Very good question. You're selecting 2. Again, here I'm counting x is the number of red balls. I'm selecting 2 balls. Okay, what are the possible values that x can take?
There are 6 red balls,
0
right?
and
There are 6 red and 1
Then
black.
0, 1, 2.
So what are the possible values I can take? I can have a red, I can have a red, black, I can have a black, red. Can I have a black, black?
No.
no, ma'am.
No,
It will
ma'am.
not happen. Okay, so what are the values there? X will take the value 1 and 2 only. Is that clear? X is equal to 0. It will start with 1. Exactly. It will not start with a 0. Is that clear?
Yes, ma'am.
Okay.
Here is x is the number of red balls.
Yeah. Black balls. Yeah,
Yes,
X is the number of red
Red
balls. I
balls.
cannot have a X is equal to 0 because I cannot have a black, black. Right. X equal to number of red balls. I cannot have, X cannot take the value 0 because X will take the value 0 means that both of them are black balls, right?
But we have
Yes,
only one
ma'am.
black
Cannot,
ball.
yeah, I can have only one black ball. So that will not happen. Is that clear?
Yes, ma'am.
Yes, ma'am.
That's why you can see that the way it is given here is m choose x. N minus M choose N minus X choose so on. All of that will take care of it there. Okay. Is that clear?
Yes.
And
Yes.
that depends
ma'am.
on what is your 2 minus I. Okay, everything has to be positive. Otherwise, I cannot define it in that way also, right? I cannot define a 3 choose I and 2 minus I if it is black and this one. So all of that will be taken care of there. Is that clear? It starts with 1.
Yes, ma'am.
Yes, ma'am.
Okay. So the next discrete distribution is what we call a Poisson distribution. 1 second. Just a minute, please. Yeah. The next distribution is what we refer to as a Poisson distribution. The Poisson distribution is where again it's a count, but this is count of events in an interval of time or interval of space. What do I mean by this? Suppose I'm interested in knowing the number of cars passing through an intersection in an interval of time, or I'm interested in number of spelling mistakes in a book or number of defects in a table. So again, what am I doing? I'm counting, but it is in an interval. I'm not, so it is a discrete random variable, but in an interval of time or space. So in that case, I'm talking about that the events are happening with a known rate. So I'm telling that the rate of cars that are going are, I know this rate, okay, and I refer to that rate typically as lambda. Lambda is again only a Greek alphabet. Nothing is going to stop you from calling it anything you want, but just conventionally we refer to it as lambda. Where what is this lambda? Lambda is nothing but the average rate at which the event, that independently of the time since the last event. Again, I'm counting the number of times this event has occurred. I call it a Poisson distribution with parameter lambda. So what is the PMF? So let's look at this. The way, again, this is from the notes only. So suppose I have a researcher who is just tabulating the the data comprising of 1000 1-minute intervals, and she counts the number of vehicles in these 1-minute intervals. So you can see that this is the type of distribution I have, and you can see from that we already know what is the frequency and relative frequency. The mean is 2.39 and the variance is 2.16. Okay. Now what you see is the number of vehicles at this traffic intersection are random and are independently of each other. The average number of vehicles per minute is 2.39 and the variance is 143. So when I am looking at the number of vehicles in an interval of time, I can model this distribution as a Poisson distribution, where the probability mass function, number of vehicles in an event of time or an interval of time, can take the value 0, 1, 2, so forth. The probability of x equal to x is given by e to the power of minus lambda, lambda to the power of x by x factorial. This e is a mathematical constant. The probability, the variance and expectation of a Poisson distribution is lambda. Okay. Both the expected and variance is equal to lambda. So from your side, you need to know what is the probability mass function, what is the expectation, what is the variance, and which situations can be modeled as a Poisson distribution. So whenever you are encountering questions which is asking you to count the number of events either in an interval of space or time, you will model it as a Poisson distribution. Okay. And this is all available in the notes, so I'm not going to repeat it because in the interest of time, we will go to the next distribution, continuous distribution. So events occurring in an interval of time, number of typos, number of defects per meter, number of vehicles passing through an intersection, number of people who are withdrawing time in a time interval, number of telephone calls received per minute. All of these can be modeled as a Poisson distribution. Any questions so far?
Clear, ma'am.
Okay. Right. So now we move on to continuous distribution. the simplest of this continuous distribution again is, now again this is just to illustrate. Okay, this is not taking a value. Suppose I have 2 points A and B, and I say that this is the density f of x is uniform within this A to B. So I mean that this f of x is taking some value k in this interval A to B. Is that clear? Uniform density is the same density throughout. Is that clear?
Yes, ma'am.
Right?
Yes, ma'am.
Okay. Now, how do I know what is this k? Now, I also know that this is the area under this curve, if this is uniform. What is the
Yes,
area under this curve? This is b minus a and this is k, right? Because this is k. What is the area of this?
B minus A
b
into
minus
K.
a, right? It's a rectangle. So the area is k into b minus a. And if this is a PDF, okay, this is a PDF, what would be the area under the curve be equal to?
1.
It will be equal to 1. So what is the value of this k? It will be 1 by b minus
B
a.
minus
Is
A.
that clear? So this probability density function takes the value 1 by b minus a. This, whether it's less than or equal to, is the same, because again continuous random variable, and 0 otherwise. Now let's plot the cumulative distribution function. For x is less than or till here, what is the value of probability density function?
0.
0.
0.
Okay, it will be 0 till it is a. At a, what is the value it is taking? 1 by b minus a, right? Now, what is the value beyond b? At b, it is taking the value 1, right? It will be, right?
At B also 0.
No, it was, see, what is the value? So, what is f of x?
After B 0.
It is minus infinity to a or x, f of x dx, right? So at, suppose at a, what will be the value? It will be minus infinity to a 1 by b minus a into dx.
Yes,
right? So what would that be?
By B minus A.
1 by b minus a by b minus a, right? What would it be at c? It would be c minus a by b minus a. It will be c minus a by b minus a. What will it be at c2? C2 minus
C2
a
minus A pound.
b minus a, right?
Yes.
So it will be nothing but a line. At b, it will be b minus a by b minus a, which is equal to 1. So you can see that the cumulative distribution function is going to be a continuous line as against the discrete line. Is that clear?
Yes.
Right?
Yes,
okay. So you can see that this is the cumulative distribution function. Okay. You can see that this is the cumulative distribution function. Is that clear? The slope is 1
Yes,
by
ma'am.
b minus a. Okay. Yeah. One of the specialized thing is what is called a standard uniform, wherein my a and b are 0 and 1. So this uniform distribution, uniform 0, 1, is some variable that you will encounter a lot when you are doing simulation, because a random number, whenever you are generating, is actually a uniform random variable between 0 and 1. What is the expectation of a random variable? If x is a uniform a to b, the expectation is a plus b by 2, and the variance is b minus a whole square by, it's not b minus a square, it is b minus a whole square by 12. I'm sorry for the typo. Okay. Right?
Ma'am, in the previous slide, even if it is beyond 1, it will be 0.
Yeah. Which will be 0?
In the previous slide you showed, right? Like otherwise 0, and between 0 to 1, it will be defined.
Yeah, this is uniform, right? Yeah, beyond 1, it will be 0. Yeah. Because it's uniform, right? It is defined only for 0 to 1. This is the curve. Beyond this one, this will be 1 by 1. 1 by b minus a, right? It is 0 everywhere else, f of x. Is that clear? Did I answer your question? Yeah.
What is f of x in this case?
It is a density function.
Density, okay, yes, ma'am.
Capital F of X will be your distribution function, and always the distribution function will take this value.
Yes, ma'am.
Okay.
Ma'am, when you took a point C in between, so what was the probability of that?
See, what is happening is, now suppose let me go through this. I have F of X, which is taking 1 by B minus A for all X between B and A. Is this clear?
Yes, ma'am.
Right?
Yes, ma'am.
Okay. Now, when X is less than A, my F of X, I'm plotting F of X. For all X less than A, it's going to take the value 0.
Yes, ma'am.
It's an A, right? Now, when it is an A, so it is basically for any A to X, F of X dx. What is that? It would be X minus A by B minus A. That is what it is, because F of X is 1 by B minus A. My integral A to X 1 by B minus A is X minus A by B minus A. Is that clear?
Yes,
ma'am.
This X minus A by B minus A is minus A by B minus A plus 1 by B minus A X.
Just explain this again.
Okay, I'll do it once more. See, I have a F of X, which is 1 by B minus A for A is less than X is less than B. Till here it's clear, right?
Yes, ma'am.
Okay.
Yes,
Now,
ma'am.
right, till it hits this A, it is going to be 0 F of X. Because how did I define F of X? F of X is probability, or F of, because I've already, is probability X is less than or equal to small x. Is that right?
Yes, ma'am.
Yes, ma'am.
Right? Now, in the continuous random variable, this would be minus infinity to X, F of X dx. By definition?
Yes, ma'am.
Yes, ma'am.
Are we considering A or X?
Doesn't matter, right? If it, let me put F of Y. Any point on the real line, F of Y is defined for any point on the real line. Because I'm not taking A here, whether it is A or B, it's any point on the real line. See, F is defined, F of X is defined for any X on the real line. Is that clear? And how am I defining? F for any point on the real line is minus infinity to that point, F of X dx. This is how my definition is.
Yes.
Or I can say minus A F of X dx. This is also fine. If you don't like A, let me call it A, B, C. Okay, C or F of P is minus infinity to P, F of X dx. Is this right?
Yes, ma'am.
Okay, yes, I put a P. Okay, now if for any P less than A, okay, it is going to be 0. Because
Yes,
F of X is not defined for those values, right?
Yes, ma'am.
Yes, ma'am.
F of X is 0 for X is less than A. So for any P less than A, it is going to be 0, right? So it will take the value 0. Yes or no?
Yes, yes.
What is the value at X equal to A? It was going to be 0, right? Okay. For X equal to, so I have a here, I have a B here. Now I have a C here, right? So I want to know what is F of C. F of C is minus infinity to C, 1 by B minus A dx. Because my F of X is 1 by B minus A.
Yes.
Now this minus infinity to A is anyway 0. I can write this as minus infinity to A, F of X dx, plus A to C F of X dx. Can I do that?
Yes.
Yes, ma'am.
This is anyway 0 because it's not
Going
defined.
from A to C.
Huh?
No, because you're going from A to B. So why do we take minus B to A?
Pardon?
We are going from A to B. Why do we have to take minus B to A for the integration?
That is minus infinity.
I'm not,
That
it
is
is
minus
minus
infinity.
infinity, not minus B. It is minus infinity.
Okay, ma'am, got it.
Okay, to A to C. So what is A to C? 1 by B minus A dx.
C minus A by B minus
C
A.
minus A, right? So for any X between A to B, it is X minus A by B minus A.
Yes, ma'am.
Yes,
Is that
ma'am.
clear?
Yes, ma'am.
Yes.
Yeah, now this
Yes,
X
ma'am.
minus A by B minus A, I can write as 1 by B minus A X minus a by b minus a, f of x is equal to that. This is the equation of a straight line.
Yes, ma'am.
Mx plus c. Right? So that's why I get a straight line. But at x equal to b, this will be b minus a by b minus a, which is going to be 1. And beyond that, it's always going to be 1. So this is the shape of my distribution function, cumulative distribution function. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So
Yes,
that is
ma'am.
why I get this cumulative distribution function, the shape of a cumulative distribution function for a uniform distribution. Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So this is how we compute the variance. Now this, again, this is a very simple thing. See, now what is the area under this entire thing?
1.
So now I see f of x is equal to 0.025. This is, so what is my density function? F of x equal to 0.025 for x is lying between 20 and 10. It is equal to 0.05 for x is between 20 and 30, and again 0.025. Is this an f of, so what is this area? It will be 10 into, so this is
0.25.
0. This is 0.25. What is this area?
0.25.
0.25 plus 0.25 is 0.5. What is this area?
0.5.
0.5.
0.5. 0.25 plus 0.5 plus 0.25 is 1.
One.
So is it a PDF?
Yes. Yes, ma'am.
Yes.
Okay, so now I can find out what is the probability. So what will be the probability x is less than or equal to 25? 25 is here.
0.5.
This is 0.25 plus 0.25. Again, it will be 0.5.
0.5.
So I can find out all these probabilities, right? Probability x is greater than 30.
0.25.
Just have to say the area, right? Of the
Yeah, it's
graph.
just the area. That's what I want you to see. Okay. So we can find out all these probabilities. Is that clear?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Another distribution is what is called the triangular distribution. Okay. Now, when you look at a triangular distribution, again, you have what is called a symmetric distribution and a non-symmetric distribution. Again, a triangular distribution, as the figure shows, it is where your PDF has a triangular shape. So the area under the triangle is going to be 1. Is that clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
I'm not going to go into this. I'll just look at the normal distribution. In the interest of time, I'm just going to skip these two distribution. I'll go to normal, or should you, do you want me to do exponential?
Yes, I think these were done in the discussion session.
Yeah,
They were-
everything. So I'll go to the normal distribution. Yeah. So this is very important, is what is the normal distribution. Again, the normal distribution has two parameters, and this is called mu, which is the center or the expected value, and the variance, which is denoted by sigma square. The density of a normal distribution is 1 divided by √2 pi sigma e to the minus x minus mu whole square by 2 sigma square. And the values a normal random variable can take is any value between minus infinity and plus infinity. Now let's look at what would happen at x equal to mu. Okay. Now at x equal to mu, what is happening when you are having the height? So when I have a x equal to mu, you can see that this, what will happen to this? So you can see that this is the shape of a normal distribution, which is bell shape. This is mu. Again, this is the spread of this distribution. And you all have already seen the approximate rule, which says that between mu minus sigma to mu plus sigma, I can expect about 68% of my observations to lie. Between mu minus 2 sigma to mu plus 2 sigma, I can expect about 95% of my observations to lie. And between mu minus 3 sigma and mu plus 3 sigma, I can expect about 99.73% of my observations to lie. Now, this is symmetric about the mean. So it follows that probability x is less than or equal to mu is equal to probability x is greater or equal to mu. Okay, so this is the approximation rule. And a distribution with mu equal to 0 and 1 is called a standard normal distribution. So what are the type of problems you want? A standard normal distribution is typically given by Z. So now you can easily see that the approximation rule says that if I want Z, so what are the values? So probability of Z lies between -1 and +1 is 0.68, approximate rule, right? This probability?
Yes, ma'am. Yes.
It lies between -2 and 2 is about 95.
Yes.
Right? So if I want probability Z is greater than -1, I'm looking at this area.
Right, ma'am.
Right? Now this area is 0.5 and this is 0.34. So this area is 0.5 plus 0.34, which is 0.84. Agreed?
Yes,
Z is greater than -1. Z is greater than 1. Is that clear? How we can do it very easily? I didn't. Now Z is greater than 1 is this area.
Yes, ma'am.
Now what is this area? This is again 0.5. This is 0.84. This area, the complement of this area.
Ma'am, from 0 to 2, will the area is not divided into half, right?
Which one? No, what were you telling? I didn't get your question.
नहीं कोकी आप खा लो फुल्का है इसका.
Hello. I didn't get the question. फुल्के के बारे में कोई बात कर रहे हैं.
No, ma'am. I was different. Can you just explain what is P Z greater than 1?
Z is greater than 1 is this area, right? Would you agree?
Yes.
Right.
Yes, ma'am.
Now this area, what is the area under the curve, total curve?
1.
It is 1. Right? So this area which I have shaded is going to be 1 minus this other area, non-shaded area.
Yes, ma'am.
Now let's look at the non-shaded area. This is 0.5, this area. Whatever I'm shading now.
Yes,
Let me show it.
Yes,
Okay?
ma'am.
Let me do it in, let me
Yes,
use
ma'am,
different colors. Let me use different colors.
Ma'am, we can use the approximations and do, right?
Yeah, that's what I'm doing with the approximation only. So let me see, this is my curve, right? I have Z is 0 here. I have Z is 1 here. Z is -1 here. I'm looking at Z is greater than 1, right? Now this Z is greater than 1 is this red area, 1 minus red area. What is this orange? What is the orange area?
0.68. 0.68.
Orange area is 0.5. What is red area? Red area is 0.34.
Yes, ma'am.
Yes, half of 0. Yes,
Yeah,
ma'am.
half of 0.68 is 0.34. So red area is 0.34. So orange plus red is 0.5 plus 0.34, which is 0.84.
Yes, ma'am.
Yes, ma'am.
This purple is 1 minus 0.84.
Yes, ma'am.
Which will be 0.16.
Yes, ma'am. Yes.
So that's what I have here. Is that clear?
Yes, ma'am.
Z is greater than 1 is 0.16. What is Z greater than 3? This area, which is almost 0, right?
Yeah.
Is that clear? How to use to find the standard normal? What is Z is less than -2?
Zero.
Less than -2. Less than -3 is 0. Less than -2.
Let's please show the slide.
0.99. There's some background.
What
Ma'am,
would
wouldn't
this
it
area
be?
What would
0.
this area be?
Ma'am, are you shading something?
No, I'm just showing this on my PDF. What is this area?
We can't see the PDF. It's still the
We
whiteboard.
cannot see the PDF. We
Okay,
are
1 second.
still on the whiteboard.
Yeah, 1 second. Now? Is the PDF
Yes,
visible?
ma'am.
Yes,
Okay.
Yes, ma'am.
Area.
Yes, ma'am.
This is 0.997 by 2. This,
Right, ma'am.
yeah,
Yes, ma'am.
right. So what would this be? This would be 0.997 by 2 minus 0.34
Yes,
minus
ma'am.
2 minus 1, right? So that
Yes,
is how
ma'am.
you can work out what are, so what would be probability Z
Ma'am, I just
is
have one doubt
minus
here.
1 and minus 2.
Ma'am, from 0 to minus 3, we have 0.997 by 2. Is from minus 1 to minus 2, 0.997 by 4.
0.95 by 2, sorry. This is 0.95 by 2. This is 0.95 by 2, not 997 by 2. Correct. This is 0.95 by 2. This is entire is 0.95, right? So only this area will be 0.95 by 2. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yeah. So you can find out for different values. You can just, you don't need anything. You can just, so what is probability? X is between 2 and 1.
0.997 minus 0.68 by 2.
This is 0.95 by 2, right? This entire area would be, what would this be? This would be 0.5 plus 0.95 by 2. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
0.95 by 2 minus 0.68
This
by
is not 0.9, this is not 0.5, this is 0.95 by 2. This entire area till 2 would be 0.95 by 2 plus 0.5. Is that clear?
Yes, ma'am.
Yes, ma'am.
Just work with the normals. See, what you need to understand is, 1 second.
Here we're taking 0.5 because we're just approximating the half of
Yeah, that's it, half.
0.997.
This half, so you can always express, that's why I'm saying, see, if I am interested in A to B, I find out what is it till B and minus A. I subtract this orange area minus the green area, I'll get the blue area. Is that clear? That's what we are doing.
Yes, ma'am.
The blue area is
Yes,
the
ma'am.
orange area minus the green area, right? That's
Yes,
what.
ma'am.
Yes,
Is
ma'am.
that clear? Okay.
Yeah.
Yes, ma'am.
And probability mod Z is greater than A is just the blue area again. So the standard normal table is what you are always, if you are given tables, you can find out what is the probability of Z is less than or equal to a particular value. And this you get from the standard normal tables. And this is what you see on the, so what is probability Z is less than or equal to 0? It's 0.5. That's something all of us know, right? And 0.1 is 0.84. We just now saw that. Less than or equal to 2 is 0.9772. So it is giving you what is the probability Z is less than or equal to a particular value. Is that clear? Yeah.
Yes, ma'am.
Another
Yes, ma'am.
type of question that you know is what is the value of X. So here, if you look at it, probability minus 3 is less than Z is less than minus 1 is the same as probability 1. So the green area is the same as the purple area, the orange area, and X I know is equal to 3. Because of symmetry, I know that this area minus 3 is less than Z is less than minus 1 is same as 1 is less than Z is less than 3 by symmetry again, right?
Yes,
Agree?
ma'am.
So X is equal to 3. So this standardizing is a very important thing. And by standardizing, I mean that if I know X is a normal variable with mean mu and variance sigma, then X minus mu by sigma is what I call the standard normal variable. So what is happening for probability X is less than A is same as X minus mu by sigma is less than A minus mu by sigma. I know X minus mu by sigma is my Z. So X is less than A is equivalent to Z is less than A minus mu by sigma. So this is what we say that, of course, why did we need standardization? Standardization has its own benefits, but I can express for any random variable with a mean mu and standard deviation as Z is less than A minus mu by sigma. One very important property of the normal distribution is if I have X and Y, which are independent normal random variables, then X plus Y is also normal. Now, this is true only for a normal distribution. What do I mean by that? Suppose I have X, which is a binomial with parameter N and P, and Y is also a binomial with parameters say N1 and P1 and N2 and P2. then x plus y need not be a binomial distribution. But here I'm saying if x and y are independent normal variable, then x plus y is also normal. This property is what we refer to as the additive property of normal variables. So if I know that x1 is a normal with say mean 25 and standard deviation 3, and x2 is also a normal with mean 30 and standard deviation 2, then I know x1 plus x2 is a normal with mean 55 and standard deviations would be square root of 9 plus 4, which is square root of 13. Is that clear? Yeah. So this is what we call the additive property. Again, I'm just going to skip this. This is also a percentile and just talked about these things. So in summary, what we have introduced today is the concept of a random variable, the probability mass function, the probability distribution function, and the cumulative distribution function. The discrete random variables, whenever we talk about any discrete random variable, we need to know what is the probability mass function, what is the cumulative distribution function, what is the expectation, and what is the variance. Same thing for continuous, what is the probability density function, what is the shape of the cumulative distribution function, what is the variance, and what is the expectation. And we looked at specific distribution, which is called the normal distribution. Okay. So I think I'll stop it here. There are a few, Prashant, there are a few questions. Mayur, are you there?
Yes, ma'am. Yes, ma'am.
Yeah. Good evening, Mayur. I think there are some questions regarding the syllabus. Can you just answer that? Couple of questions about the syllabus.
What was it? If
I
I
think
missed
some
it, like
person
I'm
has asked, is there an additional content or something? The distributions. I think that should, isn't
only the
in
normal distribution.
No,
normal distribution is
distribution.
there, right? In the
Yes,
content?
yes, it is there.
Yeah.
Yeah, it is there. It is there.
But it will not come in the exam, na?
No, it will come. So the thing is, there are three like continuous distribution. We have three. One is uniform, exponential, and normal. And for discrete, we have binomial, Poisson, and the Bernoulli. I think the Bernoulli and
Hypergeometric.
Yes.
So for the end we focus on week 9 to 12, right?
Yes, most of the questions are based on week 9 to 12, and some questions will be coming from week 1 to 8 as well. So you can think about it like as maybe 60 to 70% from 9 to 12, and from 1 to 8 we have around 40% of the questions.
40%, 1 to 8.
Yeah, 30 to 40. This kind of. Okay, so maybe we'll discuss it in the
I have
other
one
session.
doubt. Can I ask?
Yeah.
Ma'am, actually, I wanted to ask that we are studying the probabilities during in these 9 to 12, week number 9 to 12. And we had studied the probabilities prior to that also, like 6, 7, 8 using permutation combination.
See, what you do in probability is you start with the concept of a random experiment, and then you learned in those weeks what is probability of event. You mainly focused on conditional probability and computing probability of events. What we did today is we introduced a concept of a random variable and talked about the distribution of a random variable in terms of discrete distribution and continuous distribution. When we had discrete distribution, we looked at specific cases of Bernoulli, binomial, hypergeometric, and Poisson. And in continuous, we looked at uniform. We just mentioned briefly about exponential, and we looked at normal distribution. So this is what we have done.
Ma'am, I wanted to know what is the difference between what we had done prior? You are saying that that was the probability of events, and now we are concerned with this random variable. So by giving an example, can you just differentiate between the two?
Yeah, just a minute. 1 second. see, we started with this. I do not know whether you joined late or not.
I
This
was
is
there,
a-
ma'am. Yes.
Yeah, this is an element. This is a rolling a die twice. This is a sample space. Okay. So in this, I defined many events. Like I defined an event in which 1 is coming in the first toss. I defined an event in which 2 is coming in the first toss. I can define
Yes.
many events. I talked about union of events. I talked about conditional of events.
Okay.
What is the chance that the sum is 7 given the first toss is a 1, and all of that we defined, right? Now, associated with every outcome, I am giving a quantity. So now I'm not interested in events. I'm interested in an outcome or a quantity associated with the outcomes. So that's why I'm defining for every outcome, and I'm finding for every value of the random variable a relevant event. So that is the difference between random variables and events. Is that clear?
Okay, ma'am. Yes, ma'am. Yes. Thank you.
Yeah. Okay, I think it's time. So Mayur, if there are no more questions, can I shut the session?
Yes, sure, ma'am. Thank you, ma'am, for the session.
Okay, right.
Yeah.
Thank you all. Wish you all the best.
Thank you, ma'am.
Thank you so much, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank
Good
you,
night,
ma'am.
ma'am.
Thank you. Wish you all the best.
Hello.
Yeah.
Hello.
Yes, please.
Can you please let us know what will be the proportion of syllabus 70 to 48?
Okay,
I
so
missed that.
okay, maybe we have the next sessions in the upcoming week. So I'll discuss all these things in the week, right? So please don't ask the questions to Usha ma'am. So I will just take those questions in the next sessions. Okay.
Yeah. I think the syllabus and everything, the team would
Yeah.
be able to answer. Okay.
Yes, ma'am. Yeah.
Yeah. Thank
Thank
you
you,
all.
ma'am. Yeah.
Okay. All the best. Thank you all. Yeah. Thank you.
Thank you.
Bye.
Thank you.
Bye.
Bye, ma'am.
Thank you, ma'am.
Bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you all.
Good night.
Good
Good
night.
night.
Bye.
Good night.
Thank you, ma'am.
Take care. Stay safe. Yeah. Thank you.